Here's another example. Find the equation of the plane passing 1, 2, -1, 3, 2, 1, 0, -3, and 4. So basically, you're given 3 points in space, and you have to find the equation of the plane passing through those 3 points. Now, if you think about it, given 2 points, there's one unique line passing through it, right? How many points determine one unique plane?
Infinite?
No. Infinite points make up the plane. How many points determine one unique plane? That's a different question.
4?
Huh?
4?
No, you just need 3. If you have just 3 points in space, there can be only one plane passing through those 3, right? Yeah. Of course, there are some exceptions. If the 3 points are collinear, meaning that they are on a line, and then they don't determine the unique plane. So in that case, that's an exception. But usually, if you're given 3 arbitrary points, they're not going to be collinear, and therefore there should be just one unique plane passing through it. Okay? And the question is about find that plane. All right. Now let's start with the formula for the plane. It's a x minus x naught plus b y minus y naught plus c z minus z naught equal to 0. Where a comma b comma c is the normal vector, x naught, y naught, z naught is a point of the plane. Which one are we given already? Normal vector or the point of the plane? Point of the plane is already given, right? Yeah. I can use x naught, y naught, z naught as this or that. Okay. Yeah.
Is there a different process between find the equation of the plane perpendicular to the line and find the equation of the plane passing? Like you said perpendicular, does that make a difference if it's not perpendicular?
Oh, yeah, so if you're given a line equation and you're being asked to find the perpendicular plane, then we know that the direction of the line is already the perpendicular vector we want for the plane. Because what does normal mean? Normal means perpendicular. Orthogonal, normal, perpendicular, right angles, 90 degrees. It all means the same thing. Okay? Except usually when you say normal indicates there's some kind of a surface. So instead of saying perpendicular vector, we say normal vector because it's a plane, and this plane is perpendicular to a comma b comma c, the vector a comma b comma c. That's why when you're given a normal line, it's as good as just giving us a comma b comma c. Already you can use it, right? Here, we don't have such a thing. We're just given 3 points. We don't have the normal vector ready to use. Okay. We already have x naught, y naught, z naught ready to use. We don't have a comma b comma c ready to use. So we have to find that. Actually, that's the heart of this question. How can you find the normal vector to this plane when you're given 3 points? Yes?
So you have to take 1 point, subtract it from the other, and then do the same thing with a different point, and then you get 2 vectors.
Okay, so here's how it works. If I choose A, B, and C, and let's just put it on space. I don't even know where they are, but let's just say that they look like this. Okay? And then I can definitely do B minus A to get this vector, AB, and I can do C minus A to get this vector AC. And then when you get these vectors, I still need a vector that's perpendicular to these 2 vectors. How do you get that? Yes?
Take the cross product?
Yes, that's exactly what you do. Okay. So to get the normal vector a comma b comma c, the perpendicular vector, we have a very good process for us to use, which is to use the cross product. Because if we do AC cross AB or AB cross AC, whichever, I get a vector that's perpendicular to both of these vectors. And because these two vectors are on this plane that I want, it will be actually perpendicular to the plane I'm interested in. Okay? Does that make sense? All right. So we are going to do that exactly. We will do AB is B minus A. So that's 3, 2, 1. Subtract 1, 2, 1. 1 to negative 1, which is 2, 0, 2. That's AB. And then AC is C minus A, which is 0, negative 3, 4, minus 1, 2, negative 1, which is negative 1, comma negative 5, plus positive 5. And therefore, I can take my normal vector to be the cross product of these two, AB cross AC, which is ijk of 2, 0, 2, negative 1, 5, negative 5, 5, I, that's 10I, j 10 plus 2, 12, but the checkerboard of science gives you negative 12. And then k, it's negative 10. So you have 10 comma negative 12 comma negative 10 as one of the possible normal vectors. If this is normal to the plane, you can use some other multiples or divisions of this and it'll still be normal. So for example, you can take 5, negative 6, negative 5 by dividing everything by 2. It'll still be normal to the plane, right? Because it'll be the same direction. Okay? But anyways, we have one, and now we can write down the answer. We can write down the solution as 10 times x minus, let's choose this one as x naught, y naught, z naught. So it's x minus 1 minus 12, y minus 2. And then minus 10, z minus negative 1. So that's the answer. Notice that even here, you're free to divide by 2 if you want, to reduce, to make it simpler. Right? So everything's divisible by 2. I can divide everything by 2. And that's another possible answer. You could also multiply by negative if you want. I don't know why you would want to do it, but it's possible. So then, I mean, there are many different forms of this equation, which is all valid, correct answers. Yes?
So you could use like the B point for like x naught.
You can use this as x naught, y naught, z naught. You can, but at the end of the day, if you let's say you expand everything and solve for, say, sometimes a lot of times that people just solve for z. If you solve for z, you're gonna see that all of these different ways of writing it down will lead to the same exact answer.
Okay.
Any questions? All right. Let me show you a slightly different way of getting this same answer. And I like this method because it's a creative way of using the fact that determinants give you the volume of the perlopite. So here's how you think. Another solution is, suppose x comma y comma z is on this plane. X comma y comma z is the generic point on the plane which passes through these. Now, if I call this point D, right, think about the parallelopiped. So if D is on the plane, on the plane, then the parallelopiped constructed by the vectors AB, AC, and AD. So basically you have three vectors, 1, 2, 3, and using those three vectors we make a parallelopiped. What will be the volume of that parallelopiped? Of course, we're going to use the determinant to find the volume, but what will be the volume of that parallelopiped, even without calculating the parallelopiped, the determinant? What do you think? Okay, let me repeat myself. You have three vectors in general. You can make a parallelopiped, right? And you will have certain volume, right? Now, if you have three vectors which are all in the same plane, what will be the volume of the parallelopiped?
0.
Huh? It will be 0, of course, because it's flat. Can flat things have any volume? No. So then the parallelopiped constructed by these three vectors will have 0 volume. So computation-wise, it's almost the same, but I like it because it kind of uses the property of the parallelopiped. So here's how it works. You have AD, which is D minus A. So you have X minus 1, Y minus 2, Z minus negative 1. Right? And now what do? Volume is 0. So we say that 0 is equal to 2, 0, 2, negative 1, negative 5, 5, and x minus 1, y minus 2, z plus 1. And then if you compute this, you'll see that it's exactly the same as the previous answer. That's another way to